Okay, let's get started. Is this sounding better now? It feels better, right? Yeah, that's good. Some issue is resolved apparently. Okay, that's good. Looks like we didn't lose too many people. I didn't scare enough of you yet. Okay. I'm not sure if that's resolved. Yeah. Is it because of this, you think? I don't think so. Let's do some testing. No? No? Better? Turn it off? I'd like to turn it off, but Clipper. Yeah, I don't think so. Hello? Hello? Feels like there's some. No? Don't turn off. Okay. Well, I'll try to find a sweet spot here. I don't know if it exists. But, yeah. Is this normal in this room? No? Is it because of what I wear? I'll try it. I'll experiment with that later. Should we get started or should we do more experimentation? Okay, let's get started, I think. I'll try to find a sweet spot, as I said. So this is where we left off. This was the modern memory hierarchy. Going back a little bit, this was the cache in 1962. Just to gauge, did people learn about caches before? Everybody? Who did not learn about caches before? Okay, so there's some number of people. But now you know what a cache is, right? Okay, maybe you don't know the exact structure, but you know the basic idea of a cache. Okay, so caches are used very heavily. There are hierarchies of caches. These are faster and smaller, slower and bigger, even slower and even bigger, right, as you go farther from the memory hierarchy. And as I said, some of them are managed by the compiler, and some of them are managed by the hardware automatically. Most of them are actually managed by the hardware as, over here. Okay, so we're going to talk a lot about the DRAM, or main memory subsystem, so it's good to know the concepts inside this DRAM. And we're going to build bottom-up to begin with, and I'm going to give you the top-down view of it also, and we're going to switch between bottom-up and top-down. I think it's good to be able to do these. So we'll talk about rows and columns, which we already said. Talked about banks, and then build up to channels later on. But most of the DRAM that we have today is page mode DRAM. Basically, as I said earlier, a DRAM bank is a two-dimensional array of rows and columns. And in each location, you have a single bit cell. A DRAM row today is called a DRAM page also. It's unfortunate terminology, but that's how it is. This is different from a virtual page. So people should not confuse terminology, but it's already confused. But I'll try to use DRAM row mostly. And sense amplifiers, basically, these are the parts of the DRAM that amplify the data that's in the bit cell. They're called also the row buffer, because they really buffer the row when they amplify it. Remember, you activate the entire row, which brings the row into the sense amplifiers, and then it sits at the buffer over there. So you can access that row faster because it sits in the sense amplifiers once you access it. So each address that you input into the DRAM, or any kind of memory chip, is actually a row-column pair. Initially, you access a closed row, meaning that there's nothing in the row buffer. I'm going to give you an example of this later on, but you first need to open that row, send an activate command, which places the row in the row buffer. And then, after some time, the data gets stable in the sense amplifiers, and then you can send read or write commands to the column that you want in the row buffer. You don't access the entire 8 kilobytes, but you write to one cache block, for example, or 8 bytes. The granularity is something that we will talk about. Granularity, it changes a lot depending on the chip that you have. And then once you're done with the read or writes, if you want to access something else, you need to first pre-charge the array, the bank, which closes the row and prepares the bank for the next access. Essentially, these are commands: activate, read, write, and pre-charge. These are commands that you send to the DRAM chip. Now, if the row that you want is already open in the row buffer, this is called an access to a row open row, or a row hit access. There's no need for the activate command in this case. You just need to send a read or write command. So this is much faster. If you're accessing a bank that has a row open that's different from the row that you want, now you need to pre-charge the bank first, and then activate the row you want, and then do a read or write. So that's called a row conflict access, and that takes the longest. So clearly, depending on the state of the bank, the access takes different amounts of time. And I'm going to show this pictorially in a little bit. This is my view of a DRAM bank I showed you earlier, very similar to the generic bank picture that we looked at. This puts some numbers over here. You have 2 to the 14 rows, 2 to the 10 columns, 14 bits to address each one of the 2 to the 14 rows. And this is the number, basically 2 to the 24 bytes. And whenever you read, you get 2 to the 10 by 8. And it gets, when you activate a particular row, the row gets sensed and stored into the row buffer. And then you can send the column address. In this case, it's 10 bits, which addresses every 8-bit chunk of this row buffer to select which of the 8 bits that you want out of this row buffer. And 8-bit is the interface of this particular DRAM chip. This is the data out and in from the DRAM controller. And the address comes from the DRAM controller. As I said, address bits are shared. This is the pins out of the chip or into the chip. They're shared between the row address and the column address. So you send the row address first and an activate command. You wait for some time, specified by the timing constraint. And then after that, you can send a read command to a particular column address. And you save some bits. You don't send all the 24 bits at the same time in this case. And a DRAM chip consists of multiple of these banks. It's just one bank over here. And the banks, as I mentioned earlier, share the address, command, and data buses. I show all of those buses over here. Okay, it's very simple. Yes?
If I get you right, I understand that if I want only one cell in the row, I have to open the entire...
Exactly, yes. Mm-hmm. And that's part of the waste, actually. If you want... Exactly. If you want 1 bit, and actually 1 bit is not... usually, you don't get 1 bit, right? Even at the programming language level, you normally access granularity. But let's assume even if you want a byte, you still need to open the entire row, which is a lot. And that's part of the waste. But it's designed this way. Otherwise, the area cost is very high. Otherwise, you need separate row decoders for every single 8 bits. Yeah, that's a very good point, though. That's part of the waste. Part of the bandwidth waste is coming from there.
But still, most of the accesses are cache granularity. So
That's right.
It's not like you bring a single...
That's true. But even if it's cache granularity, you're right, Ronnie. Yeah, you weigh 8 kilobytes. Let's say you use 64 bytes, most of it. 8 kilobyte minus 64 divided by 8 kilobyte is wasted, which is a lot. Okay. Okay. That's correct. I'm going to get to that, actually. Exactly. From one bank, you get 8 bits. And then actually you have 8 of these chips in a rank, we will see. So you actually get 64 bits at a time. And the bus size is 64 bits. But you have something called burst mode in DRAM. In the next cycle, you get the next 64 bits. In the next cycle, you get the next 64 bits. In the next cycle, you get the next 64 bits. So it takes about 8 cycles to get 64 bytes. We will see that, actually. We're going to do the full overview. But of course, it depends, right? You can design your system to be much faster as opposed to waiting for 8 cycles. Okay, let's look at the DRAM bank operation. This is columns and rows. Basically, you have to have something in the row buffer before you access the array. So you cannot, in a sense, you cannot directly read from the array. You directly read from the sense amplifiers. Initially, this row buffer is empty. I'm going to simulate some accesses over here. Let's assume that we want to access row 0, column 0. The memory control, in this case, the memory controller realizes that the row buffer is empty. It's going to this bank. Also, I didn't show the bank over here, but there is also is an address part that's part of that specifies the bank. First, the memory controller sends row address 0 to activate the row in this bank, which brings the data into the row buffer, and it takes time to amplify the data. And the data is now strong, sensed, amplified, and now the memory controller can send the column address, the read request, or the write request. In this case, let's say it's a read. Column address 0. So, and then the appropriate column is muxed out, multiplexed out from this column mux. And then it's sent back to the memory controller. Let's assume the next access is to row 1, row 0 and column 1 in the same row. Now this is a row buffer hit. The memory controller realizes that, oh, the row is already open. So I don't need to send an activate over here. I just need to send the read command with the column address. And it gets the data again. Yes?
Why didn't you first access and pre-charge the rows?
Oh, because there was nothing here. It was empty. So you pre-charge. Empty means it's already pre-charged. So if there was something else, if there was some other row over here, then you need to pre-charge.
No, at the end of the access, after you retrieve the data. Why didn't
Oh, in this one. I see. So in this one. Because you could pre-charge, but your anticipation may be that, oh, I'm going to get another access to this row because of spatial locality. A lot of the memory controllers have that anticipation. But if your anticipation is that, oh, I don't have any spatial locality, you can actually pre-charge immediately so that you can save time. That's called a row buffer management policy, and we will talk about that also. Make sense? Another question over here? Okay, good. Yeah, we'll talk about the row buffer management policy in a little bit. So this is a hit. In this case, that anticipation was exactly correct. There was another access to column 1, and you got a row buffer hit. And the second access is much faster because of that. Let's take a look at the third access. Third access is again to the same row, column 85. That's again a row buffer hit. And you just need to send the read command with the column address, and the DRAM chip sends it back out. Let's take a look at the next access. Now it's to row 1, column 0. Memory control looks at the row buffer for this bank. It's row 0. So it needs to first pre-charge the array. This is a row buffer conflict. Pre-charging the array takes some time, which basically clears the row buffer, kind of writes back the data, at least at the high level, and activates the next row, which takes some time. Activation brings the next row into the row buffer, and then you can send the column address. So as you can see, this conflict access took much longer. So this is essentially a cache, basically. It's a required cache, because whenever you access DRAM, you can only access it from here, but it's caching the last row that you've accessed over here. So modern memory controllers actually use this as a cache and try to maximize its utility, maximize its hit rate. So this is essentially, at some level, how the bank operates. Yes?
As you said, these buffers function like a cache. And we also, the slide said that you don't recharge the row until you clear the buffer.
Uh-huh.
Because when you have a conflict. And this buffer, it's DRAM as well or SRAM?
So this buffer, we're going to get back to that. It's really more like an SRAM circuitry. But it has a lot of embellishments for sensing and amplification. But if you think about it, it's really, fundamentally, it's a cross-coupled inverter that keeps the data. Because you don't want to, you want to keep the data. You don't want to destroy the data when you access it. Here, the problem is you destroy the data when you access it. Here, you don't destroy the data when you access it. Okay? Yes?
How would you choose the dimensions of
Oh, that's you're getting into a lot of hairy things. How would you choose the dimensions of these things? Well, to maximize the capacity, certainly. So just to give you an idea, I mean, this takes area, of course, right? If you have too many of these row decoders, then you're not spending enough of your area on the columns and rows. This row buffer takes area. As I said, the size of a sense amplifier is more than 100 times the size of a DRAM cell today. So you don't want to have a lot of row buffers. We're going to go into the detail of exactly how this works. This is an abstraction, because it's assuming that a bank has a single row buffer. Even that's not true, actually, in the real design. A bank is a single row buffer that's visible to the memory controller today. That might change in the future. How would you choose the size? It's a magic equation. I'm not going to get into that, but I'd be happy to discuss that separately. Okay, but usually this is like a square. Okay, so let's go into the DRAM chip. This is a DRAM bank. DRAM chip consists of multiple banks. 8 is a common number, but it's 16 also. I mean, it changes between technologies, but fundamentally, a DRAM chip consists of multiple banks. Banks share the command address data buses. The chip itself is a narrow interface, because remember, the number of bits that you input or output of the chip determines how many pins you have. And DRAM industry has been very much focused on cost. And each pin is additional cost. They want to minimize the pins. Changing the number of banks, the size of the interface, whether or not the command address data buses are shared, has significant impact on DRAM and also system costs on top of that, which we're not going to get into. You can think about some of the trade-offs over here. This is one DRAM chip from a data sheet that I found. I guess that was a Freudian slip for a data sheet. Because some of these sheets are actually like that. You cannot get a lot of information from some of the data sheets. But I like this one, because this actually shows how things are. You can see the row address mux over here, and the different row address latches and decoders and different bank arrays over here with the real numbers, and the column decoder, the I/O gating and masking logic so that you can read the right thing, and the bank control logic, and this column address latch over here. There's a refresh counter, which we're going to talk about. A lot of DRAM systems today have auto refresh. Basically, automatically you send refresh commands at regular intervals, and DRAM knows what to refresh and how many things to refresh. There are a bunch of other things over here. As you can see, this has an 8-bit interface. But as you can see over here, this is not 8 bits. So it's actually reading 32 bits. So it's doing internal prefetching inside. Why is it doing this prefetching? Because it's using this burst mode. Every cycle, it can give you 8 bits, and you can do this for 4 cycles. As a result, it reads 32 bits, buffers them, such that it can give you 8 bits every consecutive 4 cycles. Right? That's how you get 32 bits out of this chip in 4 cycles, because it's read 32 bits. So if you widen this interface to 64 bits and kept this interface at 8 bits, then over the course of 8 cycles, you would get 8 bits, and you would get 64 bits in 8 cycles. And that's this is called an internal prefetch operation. Okay, there's more to do over here, and there's an analog part, which is also interesting, but we're not going to cover. Okay, so let's talk about rank. Basically, rank is multiple chips operated together to form a wide interface. We want a wide interface. Each chip has 8 bits, but we want to get 64 bits, so that at the end of 8 cycles, we get 64 bytes. How do we do that? Well, one way to actually increase the interface of the chip, that increases the number of pins in the chip, not good for cost. Another way is to have multiple ranks, multiple chips. All chips comprising a rank are controlled at the same time. They respond to a single command. They share the address and command buses, but provide different data. So you get 8 bits from 8 chips, but they all provide different 8 bits. So you get 64 bits at a time. A DRAM module consists of 1 or more ranks, and this is what you plug into your motherboard. And I just said this, actually. If you have chips with 8-bit interface to read 8 bytes in a single access, you use 8 chips in a single DIMM. Yes? Okay, so this is basically what it looks like. Each of them has 8 bits, and you have 8 of them, so you get 64 bits. And with burst mode, over the course of 8 cycles, you get 64 bytes. And this is my pictorial view of this from this paper, which we may cover if we get to it. So what is the advantage of a DIMM? We made the interface wider without increasing the interface of a single chip. Now we put this on like a board, right? A card over here. So these are much less costly. These are much more costly over here. So the big advantage is you gained a wider interface, and you've also gained high capacity at the same time. Maybe you didn't want that, but with wide interface comes wide capacity. And the memory controller doesn't need to deal with individual chips now. It deals with this rank. It's like a rank of soldiers. Actually, that's how it is, right? You give a command to the rank of soldiers, and they respond with different mounts, different data. The disadvantage now is granularity has increased, right? We cannot read just 8 bits. We're reading 64 bits. So we're fundamentally wasting 56 out of 64 if we just need the 8 bits. Okay. Yes?
Another disadvantage would be the fact that you couple more banks together, so you have less parallelism opportunities.
You did what?
You have less parallelism opportunities.
That's right. Basically, you coupled the banks. That's what you're saying, basically. Yes, that's true, actually. If you look at this, you coupled all of the banks together now, as opposed to having 8 banks here, 8 banks here. So instead of having 64 independent banks, you actually only have 8 banks from these chips because you coupled those banks. Because whenever you're accessing bank 0 over here, this will become more clear. You're accessing bank 0 over here, bank 0 over here, bank 0 over here also. That's a good point. That comes with this memory controller. Now it's easier for the memory controller to deal with the chips also, deal with the rank. So multiple DIMMs, if you want to increase capacity even more, this is an ugly picture, sorry about that, but you put multiple DIMMs together. This enables even higher capacity. Now the disadvantage is, how do you connect these things together? This is actually an open research topic, I think. So one way of connecting this could be using some mesh topology, such that you have different access latencies to different DIMMs. Another way could be a daisy chain, which may not be a good choice. Like fully buffered DIMM that was developed a long time ago had this daisy chain topology, which I don't think worked well, meaning that you first access this DIM, and then this DIM, and then this DIM, and then this DIM to be able to reach an address in this DIM. But that took a long time to access the last DIM over here, and you have very heterogeneous access latencies, as you can see. So interconnect is very fundamental to memory design. And this is one example where interconnect is so important in memory design, right? If you want to increase capacity, you need to somehow interconnect these chips to the DRAM control. And there's no magic here. You could have separate DIMMs connected to different channels over here, which we will also talk about, but that increases your number of pins inside the controller, which is not good. Or you could have some sort of interconnect between the DIMMs, but that now gives you heterogeneous latencies to different parts of your memory. We're going to cover interconnects. I think it's really important to know interconnects in order to design scalable systems. So scalability is certainly limited by the interconnect complexity and the energy consumption of this interconnect. Actually, FPDIM was developed, I think, maybe almost 20 years ago now, and that never took off, even though I think Intel was a big proponent of it at the time, partly because of this latency disparity. In order to access this far away DIM, I think there were 8 of them. It took a lot of latency, and partly because they had these little buffer chips called advanced memory buffers on the DIM that actually routed the request from one DIM to another, and those consumed a lot of power at the time. That could have been optimized, I think, but they did consume a lot of power. Okay, DRAM channels. Basically, channels are essentially different 64 bits, as we've discussed so far. You have memory controller controlling one channel. You could have 2 memory controllers controlling 2 channels, and these channels could be independent of each other, essentially separate. These memory controllers can be completely independent of each other, or they can be lockstep with each other. In most cases today, they're independent, so I'm not going to go over the lockstep part. Lockstep buys you another wider interface, clearly. So independent buys you basically, now you can do 2 completely different accesses to different channels. That gives you more bandwidth. And this is the generalized memory structure that we built up to, starting from this structure. Basically, in memory controller controls a channel. You can have multiple memory controllers controlling multiple channels, and each channel you have multiple DIMMs. And each DIMM you have 1 or more ranks. In this case, I show you 1 rank over here. In each rank, you have a bunch of chips, in this case 4. And in each chip, you have banks. And in each bank, you have this 2-dimensional structure, and a cache line belongs to multiple columns in that structure. And in a rank, of course, different parts of the cache line is distributed across different chips. So this is the 5-dimensional structure. It's always good to think about how data is mapped over here. We're going to get back to that in a little bit. And this is another view of it with multiple ranks. And these are some papers that I would recommend reading. Maybe some of them will be assigned as review papers later on. So these are some readings of DRAM on DRAM that I would definitely recommend. Actually, information on data sheets are very hard to extract. I think these papers that we have written clearly show how DRAM operates, at least at the very basic level. And I point out some of the sections that I find important to read, sections 1 and 2 of these papers, and sections 1 and 2 of this paper that talks about the refresh basics. So some of these may be required readings, required in the sense that you'll do some reviews, and some of these may be on the exam also, if you get the hint. Okay, we're going to cover these papers also, well, some of them. Okay, let's do the top-down view. Any other questions? Okay, now I've actually built it bottom up, even though it may not have been fully clear. I'm going to do the top-down view also to see how things are laid out. So we're going to start with the channel now. And this is one example processor over here. In this case, we picked 2 channels. It may have more channels today. As you can see, this is 1 channel. You have 2 DIMMs attached to it, and this is 1 DIMM over here. And if you look at a DIMM, you have the front and the back, and each of them form a rank. It's a collection of 8 chips over here, rank 0, rank 1. There's some circuitry over here that the memory controller reads to understand what that DIMM is, what the DRAM chips, what their characteristics are to configure the latencies. It's called serial presence detect. We may get back to it. And then this is actually rank 0 and rank 1 abstract away. As I said, they share the address, command, and data buses. So you cannot access both ranks in parallel. You need to switch between them. There's a rank switching penalty when you want to switch accesses from here to here. But it buys you higher capacity. Having more ranks gives you more capacity, as you can see. Within a rank, you have multiple chips, as we've seen earlier. This makes it more clear. You get 64 bits, but 8 bits come from different parts. And if you break down a chip into smaller portions, you get 8 banks, as you can see over here. And banks share the command, address, data buses also. you have this multiplexer over here. And if you break down the bank, we're back to this bank structure that I showed you earlier, maybe looking a little bit differently over here. You have some number of rows, some number of columns, and the row buffer and the mux. Okay, that's basically the top down. Now let's take a look at how we transfer a cache block. In order to be able to transfer a cache block, you need to map it first. And there are a bunch of mapping mechanisms. Mapping is actually very, very interesting, but we're not going to cover a lot. Let's assume the cache block is mapped to this rank 0 over here. You don't want to distribute the cache block across rank 0 and rank 1 because, as I said, you need to switch between ranks you cannot access the ranks in parallel. You have a switching penalty between them. So the 64-byte cache block is mapped to dim0, rank 0, well, channel 0, dim0, rank 0. And there's some mapping in the address bits that determines that. And let's see how we can transfer it. Basically, the first byte of the cache block comes from here, and you get 64 bits from this row 0, column 0 of the different chips. So that's how you get 8 bytes of the cache block in the first access. In the next cycle, you get the next 8 bytes, which is mapped to the row 0, column 1 of the different chips in the same bank, as you can see. And then in the next access, you get the next one. In the next access, you get the next one. So a 64-byte cache block takes 8 I/O cycles to transfer in this particular example. So hopefully it's clear, right? Every cycle, you get 8 bytes. So during the process, you read 8 columns sequentially.
So the bytes are adjacent to each other?
Could you say it again?
The bytes, every single byte
Yeah.
is 8
Adjacent to each other. I mean, in this case, we don't necessarily need to know. There might be some internal remapping. So they're not necessarily adjacent to each other, but for all practical purposes, we can assume that they're adjacent. But for internal purposes, DRAM manufacturers may do a lot of remapping of the columns internally. And also sometimes they find faults, for example, in a column, and they replace one column with another column. So in that case, it's definitely not adjacent. Okay? Okay, so let's talk about latency components a little bit. I've given you how to read a cache block, but this actually is much longer than just reading the DRAM chip, right? CPU needs to send a request to the memory controller first. Of course, you need to go through the cache hierarchy. You need to miss in all of the caches, and then you go to the memory controller. So there's some transfer time on chip to get to the controller. And then within the controller, there's some latency, which may be arbitrary because of the queuing and scheduling delay at the controller, and controller converts the access to basic commands, and we're going to talk about that. And it does reordering of the commands to maximize some sort of performance metric. And then there's a transfer time between the controller and the DRAM, which takes time, how long it takes time to access the command. And then there's the DRAM bank latency, which we've covered. Basically, this is activate, access. So in the worst case, you need to precharge, activate, and read or write. This is also called column address strobe. Is a column command. If the row is open, you just send the read or write. Row address strobe is a row command, activate. And then you send the read or write if the array is already precharged. And in the worst case, you need to precharge the array, activate the row that you want, and then send the column command. I'm using this terminology because sometimes people use this terminology. DRAM is a little bit messy. People use this sort of terminology. But basically, this is precharge, activate, read, write. In the worst case, the bank latency takes this much. And then after that, there's a transfer time between the DRAM and the controller, and this is basically the bus latency, the burst length, how long it takes. You need to take that into account. And after that, there's a transfer time from the CPU to the controller in the on-chip. And that's the round-trip access latency. So it has multiple components, and that's why the memory access latency is very long. Okay. And some of it is dominated by the interconnect, some of it is dominated by the technology. Yes? Okay. No? Okay, good. You decided not to ask. I answered it. Okay. So multiple banks and channels. As we discussed, multiple banks provide you multiple benefits, higher bandwidth. They enable concurrent DRAM accesses, and bits and address determine which bank an address resides in. Multiple independent channels serve the same purpose, except they're better. They're better in the sense that they have separate data buses, which means that you're really doubling your bandwidth or increasing your bandwidth proportionally to the number of channels. Multiple banks, in case of DRAM, you're pipelining access to the banks. You're not increasing your peak bandwidth. Enabling more concurrency clearly requires reducing the bank conflicts and channel conflicts that you have. And this is really important in the memory subsystem. That's true for on-chip also, but it's even more true for off-chip memory structures. So one of the key questions is how do you select or randomize the bank and channel indices in the address? You have this physical address. Which bits do you choose? And how do you actually randomize those bits? Usually lower order bits have more entropy because they change a lot during the run of an application. And randomizing hash functions like XOR of different address bits help in reducing the bank conflicts. We're going to talk about bank conflicts later on also. So this is one example of how multiple banks help. This is if you have a single bank, you send the address to the bank, you wait for the access, and then you can send the address only after that access is over, or you can pipeline it with the last portion of the access, as you can see, right? So this is serialized request. But if you actually 4 banks, you can start an access every cycle, and you can overlap the latency of accesses. That's how you gain benefit. You can see that 4 accesses take a long time over here. 4 accesses are done at the end over here. And if you have multiple channels, 4 channels that are completely independent of each other, then all of the accesses can start at the same time because you have 4 different address and data buses. So it's obvious, hopefully. But of course, 4 different address and data buses is more costly because you have more pins in the processor chip now. Okay, so address mapping, this is a very hairy issue, I think. But this is also a place where there could be a lot of improvement in research. How do you actually map the addresses to different parts of the memory system? I'm not going to go over this in detail, but there are 2 basic approaches. One is row interleaving, one is cache block interleaving, and there are many approaches in between that I'm going to show. In this case, for example, the bank bits are selected over here such that consecutive rows are in consecutive banks. In this case, consecutive cache blocks are in consecutive banks. I am not even showing the channels over here. So, yeah, access to consecutive cache blocks can be serviced in parallel, in this case, in different banks, and access to consecutive blocks can be serviced in pipeline manner from the same bank, in this case. So you could also imagine where the channel bits come from. I'm not going to go over that in this case, but I'm going to talk about it in the next slide. Okay, so one of the ways of reducing bank conflicts, as I said, is using some bank address randomization. As opposed to selecting fixed bits over here, in this case, for example, if your stride, let's assume, you may actually have strides that lead to bad bank conflicts if you use hard-coded bank address bits over here. But if you actually try to randomize it with XORing with some other bits over here, you can get a better bank access randomization or reduce the bank conflicts. Of course, you need to choose your hash functions nicely. You need to choose your bits nicely. And if you really want to know about this, this is a seminal paper that developed a good theory of how to interleave memory. And a lot of these techniques were actually developed initially for supercomputers because supercomputers were the ones that really pushed the need for the memory bandwidth. They wanted to get the highest bandwidth possible, and they realized that bank conflicts are really important. As I said, Cray1 was one of the first machines that actually had banked memory. It had 16 banks to cover the 11-cycle latency such that you could get 1 word every cycle. But even that was not enough. They needed to actually deal with bank conflicts, and Bob Rao talks about supercomputer memories in this case. Okay, let me keep going. Basically, address mapping gets more complicated as you increase the dimensions. As I said, memory is a 5-dimensional structure. I don't know if I have all 5 over here. I don't have ranks, for example, here. But I do have channel now, a single channel bit. Where do you put the channel bit? This clearly determines your conflict patterns, right? In this case, you basically interleave with 8 bytes. Maybe that's not good. You interleave row interleaving here. I don't even show the cache block interleaving over here, which is interesting. But cache block interleaving is somewhere in between. Basically here, half of your memory address space is in one channel, half of it is in the other channel. So your channel conflicts are clearly determined by where you choose the channel bit from. Okay, that's an exercise for you. Okay, this is another one that actually has what I wanted over here. Okay, so as you can see, there are many, many options, and this actually determines your conflict patterns. And what makes it worse is if this is not exposed to the software has no idea how to lay out the data inside the memory to get the highest performance from a system. And usually this is not very well exposed to software. As far as I know, many manufacturers don't document how they actually do the randomization inside the memory controller. I know that there are a bunch of papers that are written to actually reverse engineer that. You could reverse engineer for sure, but that's a lot of effort also. So this is one place where the communication between the memory controller and the system can be improved such that the software can do much better mapping to minimize conflicts, for example.
Could you please give
Yes.
an example to clarify the performance
Yes.
of this thing, the difference between the positioning of the channel bit
Yes.
and how it affects the interleaving?
Okay, I should repeat the question? Okay, I see. So basically, how does this affect, how does the choice of the channel bit affects the interleaving? So if you look over here, this is, I don't know, some number of bits in the address, right? 17, 32 bits. If you choose the most significant bit, what does that mean? All of the addresses that start with 0 are mapped to this channel, channel 0. Let's assume that you have 2 channels. And all of the addresses that start with 1 are mapped to this channel. So you're really partitioning your memory. Half of it, from 0 to half, is mapped here. From that half to the top is mapped here. So now your conflict patterns are determined based on that. If your memory is allocated such that you're only using half of your memory, now you're using only one channel. Basically, you wasted it. You wasted the other channel if you're not aware of that mapping. So that's one example. That's why usually channel bits are selected here. They're selected based on, let's say, cache block interleaving. That's one of the popular choices. Cache block 0 is here. 1 is in the other channel. 2 is here. 3 is in the other channel. So odd cache blocks are in one channel. Even cache blocks are in another channel. Now this may be good or may not be good. If you're accessing consecutive cache blocks, you can access them in parallel. But if you're always accessing odd cache blocks, you're still utilizing only one channel, right? You're wasting bandwidth, basically. So it's reducing the granularity of wastage, but it also depends on your access pattern. So if the software is not aware of this, or if you're not trying to minimize this wastage, you're losing performance on the table, even though your system can support much higher bandwidth. That's why this is very important. Okay, so you can actually have control over this, which we're going to talk about at the operating system level, in this example at least. So operating system influences where an address maps to in DRAM. We all know about the virtual to physical translation. You actually use virtual memory. Basically, you have this virtual address that gets translated to physical address by the processor. And physical address gets interpreted in different ways. So in this case, this is the physical address that we see. Part of it is part of the page, and part of it is the physical frame number. And this is the physical address as we use it in the memory controller. Some parts, for example, bank bits come from here. Now, the operating system determines this virtual to physical translation. So whenever it allocates a page for a given application, it basically has a virtual page number, and it allocates a physical frame for that application. If it knows that bank bits actually come from these bits in the physical frame number, it can actually allocate a particular physical row from a given bank. So it can say, oh, I'm going to, for this application, for example, I'm going to allocate physical frames from bank 0. I'm going to select physical frame numbers that have only zeros in these bits. Right. That's the idea. And for another application, it can select a bank, some other bank. Let's say a bank is bank 7. The bits that have all ones over here. This way, it can do bank partitioning, for example. It can partition the banks between different applications, which can reduce the interference between different applications. And the same is true for a channel. The same is true for a rank. I don't show the channel here. As long as, first, the bits are selected from the physical frame number, and the operating system is aware of which bits are used, and the randomization policy, of course, that's done in hardware. If the bits are selected here, the operating system has no control. For example, if the channel bit comes from here because you do cache block interleaving, the operating system doesn't have control over that channel bit, so it cannot do channel partitioning between the applications. So this is also called page coloring, basically. Whenever you're allocating a page, you choose a physical frame number of a particular color, color meaning it belongs to a particular bank or channel or rank, such that you achieve some goal. The goal may be minimizing bank conflicts, minimizing channel conflicts, minimizing rank conflicts, maximizing parallelism, minimizing inter-application interference, which we may talk about, or minimizing latency in the network. This coloring is really important, actually, assuming you can do it. Okay, so this interface is an interface where operating system has some control, but there needs to be perhaps more control over the operating system over here. Maybe having programmable addresses will be interesting, because today these addresses are relatively fixed. If you can actually make them programmable by the operating system, maybe you can achieve much better performance. But we'll get to that when we talk about some of these other researchy ideas. Okay, well, this is one of the researchy ideas that I'll cover. This paper basically uses that interface over here to partition channels across different applications to minimize interference between applications. Yes?
The previous slide is only when the operating system has knowledge of how the structure of the address inside the DRAM is,
Exactly.
which you say is usually not the case.
Usually not explicitly the case today, yes. There's information about the channel bits, but maybe not the bank bits, right? Because bank bits are usually determined by the memory controller with some randomization. It's usually not exposed, as far as I know, in most systems. You could reverse engineer. You could figure out which bits and what randomization function. And that's actually a fun project. Yes?
The structure of the address, the row, the bank, it's the controller of the DRAM is used that order, right? To know how to which row and column to access.
Exactly, yes. Mm-hmm.
But the controller is on the DIMM board, exactly on the.
So yeah, we'll talk about controllers in a little bit, actually. But the controller is on the processor chip in most systems today.
Oh.
Yeah, it's not on the DIMM. It's on the processor chip. That's actually another interface that's relatively broken today. That's limiting progress.
Yeah, because I asked that because today you can buy some brand of a DIMM and you can just plug and play it, and that's all. You don't need to configure nothing to install a DRAM.
Well, there is this serial present detect circuitry that I briefly showed inside the DIMM picture. That is the communication between the DIMM and the controller. Whenever you install the DIMM, the controller reads that and figures out what kind of a DIMM, what kind of latencies. Is it compatible? All of that. So it won't work. Any DIMM won't work with any slot, of course, right?
Yeah.
There are different DIMMs. Okay, but we're going to get back to the controller. That's the next topic, actually, very soon. Okay. So I may not talk about this, but this is for your benefit to take a look at. So you can actually do a lot of interesting tricks to reduce memory interference if you make this interface more explicit. The operating system knows and maybe even configures the mapping between virtual to DRAM address scheme. Okay. Okay, more on reducing bank conflicts. So as we discussed earlier, this is actually an abstraction also. A bank doesn't have a single row buffer. It's actually internally divided into different subarrays, but the bank, this is what's visible to the controller today. Internally, when you actually design this, you cannot have an interconnect as long as 32,000 rows over here, because if you have that, the latency would be too long. Internally, if you look at a bank, it's designed like this. It has subarrays that are relatively small, 512 rows or so, and it has basically these local bit lines. And whenever you actually want to activate a row, you go through this global decoder, latch the address, and that drives one of the rows in one subarray. And when you activate a row, it gets sensed locally. So you have this big local row buffer. Now your interconnect is much shorter, of course, over here. As a result, the latency is much better. And then how do you take out the column? Basically, you have these big, wide global bit lines that are much. So in this case, you have about 2,000, for example. But you have only 64 global bit lines, for example. So that can only take 64 out, because you don't need all 2,000. You need only 64 out that's needed. That's how you read a column, basically. The row gets latched in the local row buffer. That's how you activate the bank. And then when you do a read, you take out 64 of them with the internal prefetch that we discussed. That gets latched in this global row buffer. And those global bit lines are very wide and large, very power hungry. That's why you don't want to route many of them around. But the local bit lines are many, but they're local and short. So this is to optimize latency. But as you can see over here, there's an opportunity. Now you have 64 of these subarrays, and each of them have local row buffers because you need to have sensing circuitry in each of them. And this gives you another level of freedom that's not exploited in today's systems, but this paper makes an argument for exploiting it. The basic idea is if you have bank conflicts, if you have two accesses to the same bank, today they need to wait for each other, right? The second one needs to wait for the first one. But if they actually internally go to different subarrays, you can pipeline them also. Basically, if one access goes to this subarray and the second access goes to this subarray, there's no reason to wait for the first one to finish before starting the second one. But that requires slight modifications to the chip circuitry over here. As I said, there's a global latch today. You need to push them to be local latches over here. And you need to be able to switch. You need to be able to activate multiple local row buffers over here, which increase the power consumption slightly. But this paper shows that you get significant performance improvement if you exploit this next level of parallelism. So knowing how the underlying circuitry is designed is important to actually reduce the bank conflict. I think this is a really good idea. But DRAM interface is so hard to change, so it's not clear if this idea is going to be implemented. The Samsung and Intel paper that I mentioned earlier evaluates this idea. That was written in 2014. This was written in 2012. And they actually find benefits from that idea, showing that, oh, this is actually a good way of tolerating the long write latencies in DRAM.
We almost had that as an industry standard. It was supposed to be DDR4E, but ended up with only one DRAM manufacturer wanting to do that.
Oh, I see.
Double the number of banks using it.
They doubled the number of banks.
Yes.
I see, yeah. But this can still buy benefits beyond doubling the number of banks, right? Yeah. Yeah. Sometimes the DRAM business is very hard to change. Okay, but I think it's good to develop these ideas. So because this actually led to a lot of other ideas, and we may talk about some of the other things in a little bit. We'll talk about refresh. If you're actually refreshing one subarray, you may actually enable access to some other subarray, and that's not done today. Also, refresh in the best case today is at the bank granularity, but if you make it at the subarray granularity, you can actually get much higher performance. Okay, so this is one of the papers that I will probably require, but I haven't decided yet, so you can enjoy it right now. Okay, refresh is the next topic. This is important, and we're going to cover take some time to cover this. As I said, DRAM capacitor charge leaks over time, and the memory controller needs to read each row periodically to restore the charge. You can think of refresh as activate pre-charge every row every n milliseconds. It's not how it's done today. There used to be a time how it was exactly done this way. Memory controller was in charge of refresh. It was actually sending activate pre-charge commands every n milliseconds. But industry moved to more auto refresh today. Essentially, memory controller sends a refresh command. It doesn't know exactly what is being refreshed, and the DRAM refreshes whatever, something internally. And then the memory controller basically keeps sending refresh commands periodically. That's how it's done today. The memory controller is not in control today. Typical N is 64 milliseconds, but we're going to cover that. Basically, every 64 milliseconds, you need to refresh every single row because you don't want to lose data. This is the downside of DRAM technology. I think it's a big downside. So there are implications on performance. DRAM bank is unavailable while it's being refreshed. But as I said, if you have this subarray level granularity, maybe you can make the subarray available. You get long pause times. If you actually refresh all rows in burst, which is what used to be done a long time ago, every 64 milliseconds, the DRAM will be unavailable until the refresh ends. This is called burst refresh, which is not a good idea. I think all rows are refreshed immediately after one another. Distributed refresh is better, and it's implemented, as far as I know, in all controllers today. Each row is refreshed at different times at regular intervals, or each chunk of rows is refreshed. So this is burst refreshed. It looks bad, as you can see. You do refreshes, you cluster them, and while you're doing refreshes, you probably have zero bandwidth to access memory at this point. And after you're done, there are no refreshes for a while until the next refresh cycle. So this leads to long pause times, as you can see, because If you get a memory request before the burst of refreshes, you need to wait until the end of refreshes. Whereas distributed refresh is more like this. It's more gentle. As you can see, you're distributing the refreshes over time. Okay, so how else can we reduce the effect of refresh on performance? We're going to cover a lot of that. Can we reduce the number of refreshes? I think this is really important. If we can actually get rid of refreshes, that's actually great.
What is the idle time, relative idle time due to refresh?
If you do this.
If you take the distributed, still you have some time.
Yeah, how much? So I think of this as, yeah, how much of your throughput is lost due to refresh? That's 5, yeah, exactly. I think that's a good number. Let's say 5 to 10%. But it may increase in the future if something is not done about it. But we could actually get rid of a lot of that 5%, 10% also, I think, today. It's a big waste, I think. So it also depends on temperature. If temperature is high, you actually need to refresh every 32 milliseconds. I'm going to give you some other numbers later on. Okay, so downsides. What are the downsides? In addition to the idle time, you have energy consumption. Each refresh consumes energy. Performance degradation. The DRAM rank or bank is unavailable while it's being refreshed. Maybe some pause times during refresh. You may have a critical request. And refresh rate limits DRAM density scaling. I'm going to talk about this later on, but we're going to motivate it from a different perspective, actually, more of the reliability perspective, as opposed to this perspective. This doesn't talk about reliability, except for this last one. Reliability really affects your scaling, and that's why, but we're going to motivate it. And this is the paper, and I'm going to assign this one, I think, for sure, because I like this one. Okay, and we're going to talk about this one also. Like, one of the findings is that you don't need to actually, most cells are strong. You don't need to wait, you don't need to refresh everything every 64 milliseconds. A lot of cells can retain data for hundreds of milliseconds. And actually, people have taken advantage of it from the security perspective. If you take DRAM, make it really cold, you can actually make it have retain the data for minutes and minutes. So you can steal someone's DIMM and then put it into something really cold very quickly, and then you can recover what they have inside the memory. It's called cold boot attacks. And that basically takes advantage of the fact that retention time is not really that small in DRAM, especially at low temperatures. If you search for cold boot attacks, you'll find a lot of information on this. Okay, so basically we're going, just to foreshadow, we're going to go into it from a different perspective when we talk about reliability and security later today. Data retention time profile of DRAM actually looks like this. Very few rows need to be refreshed every 64 milliseconds. Most of the rows you can get away with refreshing every 256 milliseconds. Now that almost immediately gets rid of 75% of your refreshes, right? Because most of the rows can be refreshed at 4x longer interval. And this is true. In real life, we measured this many times. Other people have measured it. It's very interesting. It's not exploited today because we don't have the interfaces to exploit it today. The interfaces are, and maybe we don't have very reliable mechanisms to measure this today. So the caveat is, this actually is location dependent. This is dependent on the stored value. The retention time, what is this? The retention time of a cell is location dependent. It's dependent on the stored value pattern of the cell and the cells that are around it. We're going to talk about that. It's also dependent on time, meaning it changes over time. And that makes it harder to actually exploit this sort of profile. We're going to go into this. Because this is really the fundamental scaling issue of DRAM refresh. Okay, this is something that I mentioned earlier. We may cover later on. This is a good place to take, let's say, I'm fooled by the 10-minute, but with this clock as a reference until 1420.
It's now 1403.
Oh, 1403, okay. When are we done, 1430? Yeah. Do you want to take a break or continue? Okay, continue. Okay, let's do the democratic way. Who wants to take a break? Who wants to continue? Oh, this time, let's.
20 minutes.
We should have a 30-minute break somewhere. I suggest we divide it to two 15-minute break.
Okay, I see.
And we'll take one now. We'll take one in about an hour.
Okay, that sounds good. Is that okay with people? I think my TA has a good solution. I like that. 15 minutes. So with this watch, with this clock, 14:29.